Hi there. Welcome everyone to Ask Seminar Series. I'm John. I'll be moderating this seminar with Cassie, who is our communication manager. Just so you know that this seminar is being recorded and we will publish the recording on our YouTube channel. Please stay tuned and you can check it out in about a week after the seminar. And also after the presentation, we'll have the Q&A session. Please feel free to ask any questions. You can do so by muting yourself or just chat us your questions. Before the speaker gets started, I will let Cassie introduce the speaker. So Cassie, please go ahead.
Thanks, John, and thank you everyone for attending this talk. Today we're going to hear from Roger Michaelides. So he is an assistant professor of Earth, Environmental, and Planetary Sciences at Washington University in St. Louis. He is a radar geophysicist by training, interested in developing and applying novel techniques and methodologies towards studying properties of terrestrial and planetary surface processes and hydrologic systems, with a primary interest in the Arctic and periglacial landscapes. He has extensive experience working with synthetic aperture radar datasets, including time series analysis and geodetic inversion, algorithm development, error quantification, deformation modeling, and analysis. He also has experience in multi-sensor fusion of different radar operating modes over periglacial land surfaces, planetary radar altimetry, waveform analysis, and SAR signal modeling and processing. He has been a member of the NASA Above Science Team since 2016 and a member of the Decadal Survey Incubation Surface Topography and Vegetation Incubation Team since 2022. Prior to arriving at Washington University in St. Louis, he was a postdoctoral research associate in the Department of Geophysics at Colorado School of Mines from 2020 to 2022. And then he received his BA degrees in physics and science of earth systems from Cornell in 2015 and PhD in geophysics from Stanford in 2020. So without further ado, I'm going to go ahead and hand it over to Roger. So Roger, please take over.
Great. Thank you so much, Cassie and John. And so thanks again for inviting me to participate in this seminar and give this talk. I'm going to go ahead and share my screen. Can everyone see this?
Yes, that's perfect.
Okay, great. So the title of my talk today is Quantifying Permafrost Physical Properties with Radar Remote Sensing and Satellite Geodesy. And so what I would like to do is kind of give a bit of a flavor for the types of science and questions that I'm interested in looking at, most often through the lens of radar remote sensing and related remote sensing techniques. So I'll start off the talk with just a quick roadmap of some defining questions. So, we'll start off by asking what permafrost is and why it is so important. And the second question that I hope to address through this talk is, why is radar geodesy a potentially transformative technique for studying permafrost and Arctic environments? And so to really dive down and answer this question, we're going to look at 2 case studies and then a sampler of some ongoing research projects. So this first case study will be looking at permafrost and wildfire couplings resolved with InSAR. And a second case study will be looking at subsurface water saturation fraction derived from a combination of radar interferometry, polarimetry, and scatterometry. And then depending on time, I'll give some quick discussions about some current and ongoing research directions looking at Arctic coastal retreat and looking at periglacial planetary analogs resolved with EM geophysics. And so kind of the guiding scientific question I think that underpins these topics and the types of science that I do are, or I should say, is how can unconventional applications of conventional geodetic remote sensing methods enable convergent geophysical and environmental science? And so hopefully as we go through these examples, we'll see some examples of addressing this question. So to start off, what is permafrost and why is it important? If you have ever looked at one of these types of figures that gives an outline of the cryosphere, you often see these more flashy examples of things like ice sheets, sea ice, icebergs, but there is this little innocuous component of the cryosphere called permafrost, which refers to ground that is frozen for 2 or more consecutive years. So by this, we kind of mean perennially frozen ground. And this seemingly innocuous component of the cryosphere, I would argue, is actually one of the most important and potentially overlooked areas of the cryosphere, which has tremendous implications for the global climate system. So why is permafrost so important? Well, approximately a quarter of the Northern Hemisphere is underlain by permafrost. And you can see a schematic of that right here, where these different color gradations indicate how continuous or discontinuous that permafrost is. So we can see that in the northernmost latitudes, we have continuous, extensive permafrost, whereas as you transition farther to the south, it gradually transitions into discontinuous and sporadic and isolated patches of permafrost. There are also significant amounts of alpine or high altitude permafrost in places like the Himalayas, the Tibetan Plateau, and the Colorado Rockies, and we'll see some examples of those a bit later in this talk as well. So permafrost, despite only making up about 9% of the global land surface, contains more than twice the amount of bound carbon currently in the atmosphere and about 60% of the total soil carbon within all soils worldwide. So this represents a tremendous carbon reservoir in the global carbon cycle, confined to a relatively, by area and by percent, small component of the Earth's land surface. And that's potentially problematic because where this permafrost happens to be is precisely in the fastest changing region of the Earth. So the Arctic is warming at roughly 4 times the global rate. So where air temperatures are rising most severely just so happens to be where we have one of the largest carbon reservoirs in the Earth system. And as those air temperatures rise, that can promote degradation of permafrost, which can then mediate organic decomposition of that bound carbon in the soil, which can then be released into the atmosphere in the forms of greenhouse gases like carbon dioxide or methane. And so permafrost thaw and associated processes like wildfire burn are significant contributors to both greenhouse gas emissions, and they also threaten Arctic communities, ecosystems, and infrastructure. So there's this, I would argue, tremendous need to better understand how permafrost and periglacial landscapes will be expected to change over the 21st century. And so with that, to get the second question that I want to answer is, why is geodesy potentially a transformative technique for studying permafrost and Arctic environments? And the short answer for that is, oftentimes, if you want to do a detailed geophysical survey of permafrost landscapes, you usually will first turn to some flavor of in situ electromagnetic or geophysical imaging techniques, whether it's electrical resistivity, time-domain reflectometry, ground-penetrating radar. And these methods are tremendous and can shed really, really unrivaled resolution into the subsurface, but they are point-wise, they're sparse, and they're time and labor intensive. And if you want to make observations over a vast area, like at the Pan-Arctic scale, it's simply not feasible to do these EM surveys across the entirety of the Arctic. And so that is where remote sensing can potentially play a role. And the remote sensing technique that I most work with is Interferometric Synthetic Aperture Radar, which is a spaceborne radar geodetic technique that relies upon regular repeat pass SAR image acquisitions over an area of interest. If you acquire multiple radar images over a given area, you can do interferometry, by which I mean we can compare the difference in the complex phase value at a pixel by pixel basis. And that phase value associated with 2 different radar scenes is directly proportional to the change in the line of sight distance from the satellite to that particular point on the ground. What that means is if the ground moves in between when the images are acquired, we can record that as a phase difference and use that measured phase to infer the amount by which the ground deformed or moved. So InSAR as a technique is used extensively in fields like solid earth geophysics, looking at things like co-seismic earthquake strain maps, or looking at volcanic inflation and deflation events. You can also look at subtle motions associated with groundwater withdrawal and associated aquifer subsidence. So that's what we're seeing on the right here, is both the seasonal at top and then the interannual long-term subsidence over the LA basin due to large volumes of groundwater aquifer withdrawal that exceeds the natural replenishment from seasonal precipitation changes. And so what you can see is we're resolving at fairly high spatial resolution, very, very small displacements. We're talking about the order of millimeters to centimeters of ground motion. So why is InSAR potentially valuable to study permafrost? Well, permafrost by definition is underground, meaning it is hard to get quantitative and make quantitative interpretations of permafrost with most remote sensing techniques, because you are by definition looking at the surface of the earth. But with InSAR, because we are measuring ground deformation, we're actually directly sensitive to the seasonal freezing and thawing of the active layer, which is the uppermost soil layer that lies above permafrost, which seasonally freezes and thaws. And you can see an example of that in this cross-section image on the bottom here, where we have permafrost exhibiting a rather large variability in ground ice content and excess ice content, which we will return to later in this talk. Above that is the active layer, which is that soil. It too has ice in it when it's frozen in the pore space. And as air temperatures go above zero during spring thaw, that ice in the pore space melts, turns into liquid water, and because the density of liquid water is higher than frozen water, it will occupy a smaller fraction of the pore space, and so the active layer will subside by a proportionate amount. And so with InSAR measurements, if we measure differential phase measurements during the thaw season, we can relate the measured deformation, this d delta term, to the amount by which the has thawed, some incremental depth dh here. And if we make these measurements regularly over the entire thaw season, we can measure the total seasonal subsidence, which we refer to as this term D, and relate that to the total active layer thickness, which is a very important climatic and environmental parameter. So InSAR also has, I should say, fine spatial resolution and repeat temporal sampling, which are great things to have in no matter what remote sensing technique you might be using. But SAR imaging is also insensitive to atmospheric conditions, which is very valuable in the Arctic, being such a cloudy environment, which really limits your ability to image things in the optical bands. So InSAR measurements provide a unique opportunity to directly and remotely characterize the subsurface at broad scale and fine spatial resolution. With that, you can study a variety of periglacial geomorphological processes. So in addition to forming time series of ground deformation to see how the surface is freezing and thawing with time, we can also look at changes due to things like wetlands, thermokarst, which refers to the permanent degradation of massive ground ice in the subsurface and the consequent subsidence of the ground surface. But we can also look at hazards like wildfires and their impact on the landscape. And we can do all of this through a framework of geophysical inversion, whereby we collect a series of InSAR observations, which we're representing here with these delta phi variables, and forming a system of equations that relates the deformational characteristics of the landscape to some simple physical parameters, we can invert this system of equations and solve for these physical parameters. So an example of that graphically is up top here, where if we want to make a time series of ground subsidence, if we assume there's a seasonal component due to that seasonal freezing and thawing of the active layer, represented by this sawtooth pattern, we can solve for the magnitude of this seasonal component, and we can also solve for any sort of linear interannual trends due to things like thermokarst. And we can modify this system of equations dependent upon the property or process of interest. So some quick examples, we can generate time series of thaw-induced subsidence. This is an example over a portion of the north slope of Alaska here, We can see that we're resolving seasonal subsidence between 0 to 5 centimeters. We can take that and relate that to the active layer thickness at depth. And we can see that, we're resolving variation due to things like surface hydrology. So perhaps unexpectedly, we are not seeing any subsidence along these gravel riverbeds. Whereas in recently burned areas, such as the Anaktuvik River scar here, we're seeing a much higher seasonal subsidence due to the effect of that recent fire. We can also employ different techniques like spatiotemporal stacking approaches to increase our signal-to-noise ratio and generate trends or estimates of deformation rate. And so this is an example of doing that over a different complex of fires in the Yukon-Kuskokwim River Delta, where we're now resolving interannual variations in those deformation rates, in each of which cases we can also clearly resolve a higher deformation rate within these fire scars here compared to the unburned tundra. And so this is kind of leading us to the first case study I want to talk about, which is to what degree can we resolve permafrost-wildfire couplings using this InSAR technique? So for those who maybe don't think much about permafrost or wildfire, I will tell you that wildfires are actually a very important aspect of the permafrost system. They are relatively common and increasingly becoming more common. The severity and frequency of tundra wildfires is projected to increase through the 21st century. For anyone who's living on the eastern seaboard of the United States, you might remember last summer there was a period of a few days where air quality was absolutely atrocious. And if you went on, say, the New York Times, there were these cataclysmic images of red skies over Manhattan. These were all due to a series of rather severe boreal fires in the Northwest Territories in Canada. So this is one example of these wildfires having a telecommunication, if you will, or a teleconnection to more distal areas of the Earth system. But fires trigger a range of permafrost-mediated disturbance processes, including the removal of vegetation and peat, which can then trigger ecological succession. These fires also decrease your surface albedo by charring the landscape. So that can then change the thermal balance at the surface. They can alter soil hydrology and change hydrologic regimes within the area of the fire scar. They can also lead to thickening of the active layer, that seasonally freezing and thawing soil layer. If you thicken that active layer, that means over subsequent summers, you will be exposing more soil carbon to organic decomposition, which can then increase your rate of greenhouse gas emission into the atmosphere. And you can also trigger permanent thermokarst and ground subsidence, which can permanently change the landscape. So it's really important, if we want to understand the long-term implications of wildfires on permafrost landscapes, to better hone in on how these different processes play out and over what timescales we should be thinking about these processes. So as a case study example, we're going to look at a particular area in Alaska. This is in Southwest Alaska, in a region called the Yukon-Kuskokwim River Delta. So this is an area of discontinuous permafrost in the southwest of Alaska. This is a large river delta. It's approximately the size of the state of Louisiana. And it's characterized by areas of ice-rich yedema within the discontinuous permafrost zone. This is some of the warmest permafrost anywhere in the Arctic or subarctic. And it's characterized by relatively frequent fires, particularly in this lichen-dominated uplands area referred to as the Zivotnik-Kingaglia uplands. And so what we can see here is in this relatively small area, there have been a series of wildfires that have occurred over an approximately, let's say, 60 to 70 year time record, where you can see the color of the fire scar denoting the year during which the fire burned. And what you'll notice is that while we have fires going back as far to the 1950s, and in fact, we have much older fires as well, 2015 and 16 were both very big banner years, particularly 2015. It experienced about 420 square kilometers of burned tundra in this area. And so you can see, if we look at this time series of area burned, this was a relatively anomalous year compared to the last 60 or so years in the area. And You can see just how large some of these fires are. For those who are good at pattern recognition, you might recognize some of these shapes based on the data I was showing a few slides ago. So this is the landscape. This is the setting for where we are going to look at permafrost wildfire interactions. And I want to look at a particular case study that actually is looking at data that preceded that 2015 year. So we're going to be looking at just fires that burned up until about 2010 or so. And so the question we want to ask is, can we characterize any sort of residual geodetic response of permafrost responding to prior fires as a function of time since burn? In other words, if we look at the ground deformation time series over these landscapes, do we notice anything different about these fires compared to the unburned tundra? And do we notice anything that might be associated with the time since burn, or how old that burn scar might be? So to answer this question, we processed some L-band InSAR data from the ALOS satellite and complemented this with some in situ ground penetrating radar and thaw probing measurements, which were conducted in the summer of 2016. This was a part of the NASA Above field campaign and a great opportunity. This is my first time on the tundra, so it really, was a very educational experience for me. So with this data, we turn to this system of equations that I alluded to previously. And what we're going to do is solve for this seasonal deformation component, or E, which is telling us how much the ground is seasonally subsiding and then uplifting due to seasonal freeze thaw. From that seasonal subsidence, or E term, which we can see here varies from about 0 to 4 centimeters, we can also infer the active layer thickness if we pull in some additional ancillary information about things like soil moisture and the mineral content of the soils in the organic layer. You'll notice that for some of the most recent fires, so this 26 and 27 fire here, the seasonal subsidence is higher than the surroundings, indicating that that fire is causing a pronounced thaw, but you don't see a large difference. And for some of these more intermediate aged fires, they don't really appear to be all that different from the surrounding terrain. However, if we look at this interannual deformation trend, or this long-term change in subsidence, we see that the story gets a little bit more complicated. And actually, before we do that, I will first just show you a quick view of some validated in situ measurements of these active layer thickness derivations from InSAR compared to ground penetrating radar results. We can see that they agree pretty well here. And so what this is telling us with confidence is that this separation that we're forming is doing a good job of separating that seasonal component of deformation from these long-term deformation trends. So once we've separated that seasonal term, if we look at the interannual deformation term, we see a much different story. And so what I'm showing here now is this subsidence trend with units of centimeters per year. Positive values are telling us that the trend over this area is an increase in subsidence year by year. So where the ground is subsiding more and more. Blue values indicate uplift trends. So the ground is slowly rebounding over the years. And I've put at left here, again, this image of the fire scar age. And what you'll notice is that there's a pretty clear spatiotemporal correlation between fire age and this interannual deformation rate, whereby these more recent fires are much redder. Intermediate aged fires are white. There's really no statistically significant in your interannual component. And some of the oldest fires, these 1971 and 72 fires, are actually indicating a small uplift time. And so if we plot these subsidence trends as a function of time since burn, we see that there's this pretty clear exponential relationship between subsidence trend and time since burn. And so what we think is we're really decoupling the active layer and permafrost responses to get a sense for how the permafrost at depth is responding to this fire perturbation. And so by separating out that transient response of the active layer, which it turns out we can also fit data to, we can then estimate the time it takes for this system to recover to its pre-fire condition. And so what we're seeing is that it would appear that it takes the active layer at the surface to take about 20 years to recover to its pre-fire thermal state, whereas the permafrost at depth undergoes a process of gradual degradation and then gradual reaggradation mediated by ecological succession that plays out over about 70 years or so. And so the model that we're proposing here is that when you have a fire that burns off some of the organic layer and vegetation at the surface, you change the albedo, and you also remove some of that thermally insulative organic soil. That is going to change the thermal equilibrium of this one-dimensional soil column, which is going to promote thicker active layers, deeper seasonal thaw, which will persist over many years. But in parallel, you have this process of vegetation and ecological succession, whereby pioneer species are coming in, recolonizing the burn scar, and gradually building up that organic layer and returning the surface albedo to a more greener state, which will slowly recover that thermal insulation and gradually and slowly promote permafrost reaggradation. And so at some point, you will eventually return to your pre-fire thermal condition. And so again, by separating the active layer and permafrost responses, we can look at two different timescales of recovery, this shorter active layer recovery process and this longer scale permafrost recovery process. And if we turn now to ecological studies, we can see that the results that we're getting here, the timescale of recovery is consistent with independent ecological studies, looking at ecological succession over some fire scars in the same area. We're looking at the time by which different species like lichens return to the fire scar, when vascular plants start to show up again versus when shrubs arrive. And this is consistent, again, this time scale is consistent with this process that we're seeing with InSAR, which is exciting as someone who isn't trained really to think much or to know much about ecology. It's exciting to see that these geophysical measurements are telling a similar story. So that is one case study. I now want to turn to a second case study of what InSAR can tell us about permafrost by looking at resolving subsurface saturation fraction of water using a combination of radar interferometry, polarimetry, and scatterometry. And so the motivation for this question is that surface soil moisture and near surface soil moisture, so we're talking within the first few centimeters at depth, are actually rather tightly correlated with a lot of the InSAR-derived ground deformation measurements that we care about in permafrost landscapes. What I mean by that is soil moisture in permafrost landscapes exhibits a seasonal time dependence. In other words, as your thaw season progresses, oftentimes areas of the tundra become wetter over the thaw season. And that is going to correlate with the surface deformation signal that we expect as well. As the active layer is thawing out, our ground is deforming, but it's also getting inundated and wetter. And so we have these two competing processes that are playing out at roughly the same time scale and can potentially be aliased onto each other. It's further compounded by the fact that changes in soil moisture content can actually induce physical changes in the measured phase that we use as our primary input for geodetic measurements. And so if we have changes in soil moisture, that can then further bias our estimates of ground motion. So we would really like, in a perfect world, to be able to separately resolve the dielectric changes associated with changing soil moisture from any of the geodetic ground motion associated with ground thaw. And if we can do that, in principle, we should be able to yield higher fidelity estimates, not only of freeze-thaw dynamics, but also seasonal thaw depth and the seasonal behavior of moisture within the permafrost active layer. And so, to motivate this again, we're looking again at some data over the 2015 fire scars in the YK Delta. And what you'll notice is then for these 2015 fire scars seen here, here, and here, they have a much higher surface water saturation fraction than the unburned tundra. And this is consistent with field measurements as well. And what we see in the field, as you have these fires, you basically reduce transpiration because you've burned off vegetation, and you also have pooling of water due to the melting of excess ground ice content. However, we would like to separate the signal because we also expect to see deeper subsidence in these burn scars. So how can we do that, and why do we care? Again, this is giving us a sense for the degree of that uncertainty in our geodetic measurements, and if we want to infer something like active layer thickness from InSAR measurements, our measured InSAR deformation, this d delta term, is going to be linearly related to the incremental thaw depth of the active layer, like on that graphic I showed earlier. And they're related by the densities of water and liquid ice, liquid and solid water, as well as the porosity and saturation of the one-dimensional soil column. And we can form this integral and estimate the active layer thickness like so. But if we have changes in the saturation fraction, or in other words, how wet the soil is, that can introduce large errors into what our retrieved active layer thickness is, on the order of about 5 times if we have very, very, very dry soil, for example. So we really want to have a better understanding of soil moisture and how it varies spatially if we want to develop, robust estimates of active layer thickness at an operational or regional scale. So one way we can do this is combine different radar imaging modalities. And so what I'm showing here is a combination of radar interferometry, which we've talked about previously, and radar polarimetry, which looks at the polarimetric backscatter of the radar signal. In other words, how strong is the reflected signal at different polarization states, which can be used to look at variations due to vegetation as well as soil moisture. And so there are several physical models that can relate these different polarization states to things like soil moisture, among other things. And so, without going too much into the details here, if we measure the co and cross polarized backscatter ratios over some landscapes, we can fit these into physical models that relate these radar backscatters to things like the thaw depth, the saturation state, and the dielectric profile with depth over the landscape. We can take independently acquired measurements of ground subsidence from L-band interferometry and P-band, which is a lower frequency, larger wavelength radar, polarimetric radar, to look at these cross and co-polarized backscatter values. We can combine all these measurements into a modeling approach and into an inversion approach and solve for estimates of surface saturation fraction, water table depth, thaw depth, and surface roughness as well, all with uncertainties associated with these values. And so what we're seeing at right here are the results of this modeling framework, I should say inversion framework, where we've solved for seasonal subsidence, active layer saturation fraction, and the active layer thickness as well over this area in the YK delta that was impacted by these fires. And so this was part of the NASA Above Airborne campaign, which first flew in 2017, and it is still collecting data. They just acquired data a few weeks ago. And the data that we've processed here is, again, airborne L-band, InSAR, and P-band polarimetric data, which was collected in the summer of 2017 over the above study domain, which is shown here. So all of these orange boxes here correspond to the individual flight paths that were surveyed that have co-registered L-band and P-band data. And I'm also showing, just for context, where existing in situ validation data is available, either through above field sites or calm field sites. And so we can see that we have field data to independently verify a lot of this airborne data, but not all of it. There are some areas where we don't have as much in situ data. But applying this, this joint inversion technique of L-band, InSAR, and P-band PolSAR, we can generate a 30-meter co-registered product of estimated seasonal subsidence, active layer thickness, volumetric water content, and other associated geophysical variables for all 51 of these flight lines across Alaska and Canada. And if you're interested in checking out this data, I've included a link here to the data archive for that data set. It's publicly available, as are the papers that describe the processing techniques for how this data was generated. Cool. So those are 2 case studies. I now want to give 2 more kind of quick little research samplers of some current and ongoing research that I'm involved with that is looking at other ways that we can study aspects of periglacial landscapes using either radar or geodetic imaging techniques. And so we'll look at 2 examples, the first being Arctic coastal retreat, and the second looking at planetary analog features in periglacial landscapes using a combination of geodetic imaging and in situ EM geophysical imaging. So this first example of Arctic coastal erosion and retreat is again motivated by this fact that the Arctic is warming at roughly 4 times the global rate, which can lead to widespread permafrost degradation, ground subsidence, coastal inundation, and coastline retreat. In some cases, these retreat rates can exceed 30 to 40 meters per year in some location. So we're talking about incredibly rapid retreat rates that are changing fundamentally the landscape at an annual or subannual basis. We can see some examples of what this looks like on these figures here from this paper by Ben Jones, where we're seeing how we can have massive block failure and collapse features where we have massive blocks of permafrost that will just mechanically break off or slough off of the coast as you're thawing out that permafrost and melting excess ground ice that is acting to bond this landscape. But once the ice melts, you're basically transitioning from cement to an unconsolidated mud. And so you can see that these are rather large collapse events that can dramatically result in large erosion and retreat rates, more or less instantaneously or over a single thaw season. Now, these retreat rates are mediated not only by thermodenudation or atmospheric forcing, so this is the air temperature mediated thaw of permafrost, which can change the mechanics of the coastline, but also thermoabrasion or oceanic forcing. So wave action can also act to erode coastlines and impart thermal energy into the coast as well. In all of these cases, near surface ground ice content plays a very large role in modulating what thaw-induced subsidence and coastal retreat looks like. So in areas with high ground ice content, one can experience very marked and dramatic coastal erosion and retreat rates. And so to get a better understanding of how Arctic coastal erosion might play out in the future, it's really necessary to have a better idea of how ground ice content varies at broad spatial scales. And so one way of addressing this question is by combining different imaging techniques to try and better infer the geomorphology of how these coastal erosion and retreats progress. And so this is an example of research that is being led by Marnie Bryant, who is a graduate student at Scripps, UCSD. And what Marnie is doing here is combining high-resolution optical imagery from Planet Labs imagery and performing a thresholding operation to generate high-resolution estimates of the coastline at different times. And so what we can see here are estimates of the coastline over a relatively small area acquired in 2019, 2020, 2021, and 2022. You can see that the coastline is being identified in each of these cases. And we can look and see how that coastline is changing with time to infer retreat rates. In other words, how far is the coast retreating southward? And so that gives us an idea of the plan form retreat of these coastlines. But what Marty's also doing, which is particularly exciting, is looking at laser altimetry from spaceborne LiDAR. This is from the ICESat-2 spaceborne mission. And what this provides us is topographic transects, or almost perpendicular profiles from the coast onshore, which gives us a sense for the three-dimensional topography over these coastlines. And what this is now giving us is an understanding of the process by which these coastlines retreat. And so I've 3 examples here, all acquired within a kilometer or 2 of each other. And you can see that there's a considerable variability of erosion modality, I guess I should say. So, in this example here, we're seeing a rather gradual bluff retreat. As those bluffs break off and slump into the ocean, the coast retreats. But then nearby, we see areas that are perhaps being impacted by things like surface inundation or coastal inundation of water. And then other areas where the coastline seems to be buffered and not really retreating noticeably, at least over this observational record. So we're really seeing marked changes in retreat over incredibly small spatial scales, several kilometers. And this is really hinting at the complexity of this process. Part of that complexity, again, is driven by variation in ground ice content. And so some work that my graduate student, Alex Wynn, here at WashU is doing is trying to see if we can place constraints on excess ground ice content in some of these coastal environments and see if we can use that to identify areas of the coastline that might be susceptible to future rapid retreat. And so without getting into the details here, what Alex is doing is introducing a depth-dependent parameterization of excess ground ice content to the existing physical models that we use that relate measured ground subsidence to inferred active layer thaw depth or seasonal subsidence. And so the idea here is by introducing this parameterization, we can estimate the amount of excess ice content within the active layer. And we would expect areas of higher excess ice content to, erode more spectacularly and perhaps have the potential for higher bluff failure and mass wasting events. And so by doing this technique, Alex is generating these estimates of excess ice content within the active layer over this same study site that we were looking at previously from Marnie's work. And then we can also look at annual subsidence range and changes in coherence in conjunction with these excess ice content maps to identify locations where we think the coastline may be particularly susceptible to future rapid retreat. And of course, this is motivated in part by the fact that there are many communities on these coastlines that are having to actually physically relocate, in some cases, their communities because this widespread coastal retreat is causing buildings, in some cases, to literally be swept into the sea. So there's a strong social dimension to this work as well, beyond just the kind of earth science type research here. I now want to talk very briefly about some analog work that I'm increasingly getting more involved with in my group here. So this is some planetary science analog work. Actually, before I started thinking about permafrost, when I was an undergrad researcher, I was doing some research in a planetary science group. And so planetary science has always been kind of near and dear to my heart. And it's actually, in fact, the reason I got interested in periglacial landscapes on Earth is just because they are such exotic landscapes with interesting landforms. And so this is some work that is being led by Tyler Meng, who is a postdoctoral research associate in my group. He recently received his PhD from University of Arizona, where he was looking at rock-covered and debris-covered glaciers on Earth as an analog for analogous features that we see in Mars. And so the motivating question here is, there are these puzzling features on Mars, which we think can inform an understanding of what past climatic conditions were like on Mars, basically getting at the question of a wet versus a cold Mars. And what was the time scale by which these climate changes occurred across Mars? How widespread was surface water or ground ice in different climatic regimes? And so by looking at these features on Earth, we can get a better understanding of how to interpret them visually from satellite data sets. And to set the landscape here a bit, for those who don't often think about these features, there's a bit of a spectrum or a continuum between these features. By debris-covered glaciers, we usually refer to features that have a glacial origin, meaning they are more or less similar to most glaciers that you would think of. They have a original ice stratigraphy that is still intact. However, they are covered by a thin supraglacial debris cover, in some cases even less than about a meter, and that is what gives them this degree-covered moniker. Contrast that with what we refer to as rock glaciers, which are fundamentally periglacial in origin, meaning they are more or less unconsolidated sediments that you might find in a landslide, but they are bonded by ice. So they are subject to freeze-thaw dynamics and melt infiltration. They generally have a thicker debris cover, usually more than 2 meters or so, lower ice content because their origin is not as an ice glacier, but rather as a periglacial feature. And that ice is distributed either interstitially or in deep discontinuous ice cores spread throughout the feature. Superficially, these features can often resemble each other, but depending on if they are debris covered or rock glaciers, that can have dramatic differences into their dynamics and kinematics, as well as their formation mechanisms. And so one question Tyler is interested in is, are the surface features that we often see on these flow features, which are usually perpendicular to the flow direction, are they surface ridges due to compressional and extensional buckling, or are they climatic oscillations, which is telling us something about the flow regime and dynamics of these features in different climate epochs? And to answer this question, what Tyler looks at is a combination of static geophysical imaging, so looking at composition and subsurface structure from ground penetrating radar. We can see an example of that here on the left, where we're very nicely resolving some of these in-glacial reflectors, which are associated with variations in ground ice content or debris layers. And Tyler's using radar travel time measurements with a bistatic antenna configuration to calculate the subsurface geometry. So what is the spatial distribution of ice and debris thickness, as well as estimating ice fraction of the subsurface. So by fraction, how much of this volume is ice versus debris. To do this well, you really need accurate radio wave speed measurements, which can be done if you have these multi-antenna bistatic or multistatic acquisitions. And so here's some data over a series of features across Colorado, Wyoming, and Alaska, showing the diversity of ice fraction here as we transition from rock glaciers into debris-covered glaciers on the right end of the spectrum, with an associated change in both ice fraction and wave speed velocity. We can also, however, look at the kinematics and dynamics of these features. So in other words, how are these features changing with time? And so this is an example, again, from Tyler's work using stereophotogrammetric change detection. And so this is repeat imagery that was acquired by drones, so very high resolution drone imagery. And by doing change detection, we can generate these structure for motion maps, which tell us how the surface is displacing or deforming over time. So these are displacement maps. This is, planform displacement in this case, rather than line of sight displacement, which we normally get with InSAR measurements. But we can use these as well to look at elevation changes interannually, which I'm showing here, as well as an east to west profile across this glacier feature. And you can see that there are systematic differences in the off-glacier and on-glacier elevation change associated with the dynamics of how these debris glaciers are deforming with time. We can also, using this photogrammetric imagery, infer strain rate estimates. And so what I'm showing here now is a map of inferred strain rate across this feature from areas of no significant strain to both compressional in red and extensional in blue areas. And you'll notice that we have this repeating pattern of compression and extension, particularly in these areas where our ice thickness is where our debris thickness is rather low and where we have high ice content. And so what this is telling us is that at least for some of these debris-covered rock glaciers, these transverse ridges that we're seeing are likely due to the kinematics. They're extensional and compressional features rather than a climatic feature. And so this sort of analysis can then inform how we interpret these features on Mars or elsewhere in the solar system. One last example of a planetary analog. This is work that was done by Venetia Folingstad when she was an undergrad while I was a postdoc at Colorado School of Mines. She's now doing a PhD at University of Oregon. And so this was work looking at pingos, which are these exotic ice-cored massive hill features that we see in periglacial landscapes that form due to basically pressurized artesian groundwater that focuses groundwater to a particular region that then freezes, and you form these cores of solid ice that will gradually jack up the landscape. So you can I always say that these are kind of like permafrost, pimples, if you will. And they've been invoked previously to explain features that have been observed on other solar system bodies like Ceres, but also features on Ganymede, Europa, and Mars as well. And so what we wanted to do is see if we could combine InSAR measurements with EM geophysical imaging to get a better understanding of how these features evolve with time. And so what I'm showing here is data this is ground penetrating radar data that was acquired over a series of pingos on the Alaskan North Slope. This is a video just of that data acquisition using a multi-static GPR configuration being towed by this snowmobile here. And you can see that we're resolving this really, really clear, and I think it's beautiful at least, massive ice core in the center of this pingo. It's about 11 meters thick of ice. By being able to image and resolve the geometry of this ice feature, we can infer the age of this pingo if we make some assumptions about the ice accretion rates. And if we compare this to a time series of cumulative surface uplift over this pingo acquired from InSAR data, which I'm showing here with these black dots from about 2017 to 2021, we see gradual uplift of around 8 centimeters or so, which is consistent with the same physical model of ice accretion if we assume that that ice is accreting via Stephan's equation style law, which is one of the more commonly invoked models for measuring ice accretion used in cryospheric sciences. So what this is telling us is that these two imaging modalities, subsurface geophysical imaging and radar geodetic imaging from space, are shedding complementary information on the dynamics of this feature, and they're telling a consistent story. And so these results can then be used to not only understand how these pingo features might evolve on the terrestrial landscape, but also give information to planetary scientists about how they might be thinking about these invoked analogous features elsewhere in the solar system. So with that, I will kind of end here. And again, just remind you all that the type of work that I really like to do, I kind of like to phrase as unconventional applications of conventional geodetic remote sensing methods, with the idea being, can we enable convergent geophysical and environmental science? These were some of the topics that we looked at today. And I'll just mention as well that there's many more exciting projects that are being done by members of the Radar Remote Sensing Lab here at WashU, as well as other collaborators at other institutions. And so really, this work is all theirs as much as it is mine, and I just want to acknowledge them there. And so with that, I'm happy to take any questions. So thanks so much for listening.
Thanks, Roger. That's a very comprehensive and very impressive talk, not over results. So any other questions?
I have a question. Roger, on the Pingo GPR survey, what frequency GPR did you use to penetrate that deep?
Yeah, so that image that I was showing was a 100 megahertz GPR. Let me pull it back up. So this was 100 megahertz. But we acquired data at 100 megahertz, 200 megahertz, and 50 megahertz. Generally speaking, the lower in frequency you go, the deeper your effective penetration depth is. By contrast, if we're thinking about, these radar images at C-band and L-band, we're thinking in the range of about 1 gigahertz. So orders of magnitude difference in frequency. I guess I should say order of magnitude, but yeah.
Any other questions?
I do see a question in the chat. I guess they're saying, how can these measurements be useful for hydrological modeling, and if these data are available for public use? So yeah, I think these measurements certainly can be of interest for hydrological modeling, particularly if you're looking in periglacial landscapes. And so the data that I was showing, that airborne data from the NASA Above campaign, is all publicly accessible. I will include a link to the data set in the chat there if you want to check it out. I don't know if that might just be an image, which is not very helpful. But let me see if I can get the actual text here. And then actually Kevin Schaefer, who asked the first question about the pingos, was the PI for this project. So he can also answer any questions you might have about that particular data set. But yes, they are publicly available, and I think of interest and use for hydrological modeling.
Okay, actually, I got two questions. One is that is it possible to get the phase information from the InSAR from like GNSS, the satellite? That's my first question, and my second one is I think I came across to a seminar a while ago about so the speaker was proposing some new future satellite missions, and the idea is about using two satellite, and so the transmitter is on one satellite and receiver is on the other one. So I wonder, like, what's new information can this kind of concept bring in compared to the traditional one satellite InSAR?
Yeah, for sure. So for your first question, GNSS certainly can be used to look at permafrost dynamics. There has been some work done in that previously. In addition to looking at the dynamics of seasonal thaw, subsidence, and uplift, you can also do GNSS reflectometry to try and infer things, again, like soil moisture or perhaps snow cover, if you're looking at an area that has persistent snow in the Arctic. And then for your second question, I'm not totally sure what potential mission it might have been, but if it was a bistatic radar mission, something analogous to either like SRTM, which was flown on one of the space shuttles to get topography, or perhaps something that might be a repeat pass bistatic configuration. In both cases, they would shed new light into how we think about permafrost landscapes. For bistatic configurations, that would be really great for separating and resolving surface topography and vegetation, particularly in vegetated areas and permafrost landscapes that can introduce biases into the inferred phase measurements. And then for repeat pass bistatic configurations, if your transmitter and receiver are in different physical locations in space, you're actually now sensitive to a change in the scattering physics. And so you can use that to actually constrain the orientation of scattering elements on the surface. So, can you perhaps discriminate between different vegetation types in a tundra, or use the change in the reflectivity to infer something about soil moisture configuration? And then, of course, you can also do conventional kind of InSAR geodesy as well, if these are phase sensitive measurements and the baseline isn't too large. So hopefully that answers your question. But yeah, I think a lot of potentially cool and innovative things still to be done in permafrost and remote sensing more generally.
Okay, that's good. So any other questions? Actually, we have over 20 attendees and peak. So unless I'm interrupted, let's thank the speaker again for giving the great talk, and I want to thank the attendees for showing up. So we have 3 more seminars coming up, so stay tuned. Thank you.
Thank you, and thanks everyone for coming.